Greetings, 216ers. This is Professor Kaufman, and what follows is a video overview of your second project for the course. Fair warning, this project, though it's divided into three problems as the first one was, is significantly more challenging than the first project. So particularly if you ran into time crunch problems towards the end of project one, it would be wise to start as early as possible on this one. The very last problem, which implements a small application in C, has proved challenging for past students, and that's especially true if you're a little rusty on your binary search trees. So make sure to save enough time. We'll touch on each of these problems in sequence. Roughly speaking, they are separate and distinct and can be worked on in any order, but as usual, going in order is probably sensible. The first problem is going to pertain to utilizing bit-level operations in a semi-practical setting that mirrors what you do in an embedded programming setting, at least to some extent. The second problem is going to have you solve a puzzle of sorts, which will teach you about debugging and use of the GNU debugger. It's my understanding from in-class responses that many of you have already seen debuggers, so this shouldn't prove terribly difficult, but it'll acquaint you with how to do so in C. And then, of course, the last problem, as I mentioned a minute ago, it has to do with building a small tree set application. If you're not acquainted with tree sets, we'll have a quick review on that. So I'm going to presume you're now acquainted with some of the conventions. For instance, there's a code pack up top here, and you'll want to download it to the location that you plan to work on it, likely Grace, although there are other mechanisms. And I'll presume at this point that you've got your coding environment set up reasonably well so that you can get the zip and start cranking away on the code. The manifest for the project, well, I should say the convention is the same. There's a makefile, there's some automated tests, and there's some manual grading criteria there we'll touch on. But the manifest down here lists the files that are associated with each of the problems, and they each have their own little flavor associated with them. So let's start with problem one, which features use of bits in a battery meter simulation. I'm going to fast forward down a little ways so that you get an idea of what we're up against here. Essentially what you're going to be coding is the underlying logic to create a little display that looks like this. This isn't a class that deals with graphics in any sense, so we'll provide a little simulator for this. It doesn't quite look like this because it's done in a text terminal, but no matter. But the central idea is that in small embedded devices, like little watches or some little device like the microphones that I use to record in-class lectures that are wireless, they have a little battery meter on them. Typically, this looks at the voltage level using some low-level hardware detectors and detects a certain voltage level that's coming off of the battery. And over time, as the battery loses its charge, that voltage level drops. And so there's a formula that equates a voltage level to a percent fullness of the battery. With that sensor value in hand, the idea is then to create a visual display that's a little bit more consumer friendly. Some of you may be totally hip to the world of electrical engineering and be able to do voltage translations yourself or know what typical voltage levels are for such devices, but most of the rest of the world, myself included, prefer a percentage over here. Now, in little embedded systems, like the one the size of the little dumb pack that I use for the wireless recording stuff, you need pretty small chips with very limited capabilities in order for them to be cheap enough for consumers to buy. And that means you don't have big standard libraries for anything, and you do more at the bit level, particularly as you'd interact with primitive little devices like LCD displays like this. Now here, there's a bunch of little lights, and some of them are not lit up, so there's a blank over here, but there could be something there. Whereas here, there's something that has been lit up to indicate that this is part of a number. You can see one of the classic sort of applications of this stuff is, there's some number of panels over here. There's 1, 2, 3, 4, 5, 6, 7, a little 7-panel LCD display that allows digits 0 to 9 to be displayed with reasonable readability. This is the kind of display that you might work with in an embedded setting, as well as there's some parts over here that correspond to a visual battery meter that if a particular bar is on, then it'll show a light right here. And if you show them in the right sequence, then it can sort of correspond to a visual indicator of how full the battery is. Not very full in this case, at 49%. Very full in this case, so apparently 4.23 volts is full up. So the V over here indicates the display is in volts, and the percent, which is dimmed here but live here, indicates the whole business is being shown in percentage. Now all that as a problem domain then starts to speak to the special techniques that are needed. Essentially, this is a series of lights that are on and off, and oftentimes this is presented in an embedded setting as if a particular bit is set, then this light goes on. It's not on right now, so there must be a 0 there. And you can see the 10 up here corresponds to this 10th bit in a particular number they'll manipulate. It's a 0, so this light's off, versus the next number, 11, that's on, showing this. Now what that means, if you turn on bits in a certain pattern, in this case from right to left, 1, 1, 1, 1, 0, 1, 1, then you'll see a 9 on the screen. Even though this set of bits has nothing to do with the number 9 in any encoding, 2's complement or otherwise, the meaning of them in their whole is not so much to convey 9 as to turn on a series of lights that are tied to give a human impression of a 9 there. So too then certain bits correspond to other things, like over here there are some bits that will turn on the voltage or turn on the percent or turn on the little decimal place here. Not used in this percentage mode, but is used always in the voltage mode. As well as then some of the high bits here, the 28th, 27th, 26th, etc., they correspond to the levels here of the visual battery indicator. There's a few other examples of these over here, including some extreme cases. But what you would start to recognize if you look at these is that this complex series of 1s and 0s can be subdivided somewhat into, if I wanted to display a 1 here, I would take this series of bits, 0, 1, 1, 0, 0, 0, 0, and scooch it over just a little ways, past starting at this 3th bit right here. If I instead wanted to display a 1 in this position, then I just scooch that same set of bits over a little farther, so they started at the 10th spot. And you're starting to see now, those bitwise operations of masking and shifting and ORing and so forth, those things will be useful in this context as they'll allow you to create this pattern in a somewhat programmatic fashion. There'll be some special cases associated with how to set up the little visual battery indicator, but there are a bunch of notes about that down there. Just to back up a little bit, the way this will be presented in a C program is as follows. The hardware will have a sensor on it that is tied to some data input and is presented in the C program as a global variable that's called bat voltage port. It's a short, so it's a 16-bit number, and it will show the voltage level that's read off this sensor according to a certain scheme over here. That reads it in half millivolts, so every count of 2 is 0.001 volts over there, and it'll make for some shifting operations. And part of the job then is to convert this raw sensor value into some sensible voltage level, and then correspond that voltage level to a little display over here of there's a formula that allows me to convert how many volts equals what percentage full is the battery. And according to the charts, if you hit 3.0 volts, then that's going to be empty. But anything above 3.8 volts, that's fully charged. And that's a typical logic range of about 3.3 volts is what a high sort of level of logic is. And if you sort of go below that, a lot of digital devices in the embedded settings start to not work anymore, including processors for that matter. So when you drop below this voltage, there's an automatic sort of kill switch that engages and turns the device off so as not to permanently damage the rechargeable battery or produce miscreant results. There's a formula given here then to say, oh, if I take this global variable in my C program and I need to convert it, then I just use this formula, and this gets me the battery percentage along with, the battery voltage, and then convert that to the percentage over here. And you'll notice some operations that are dividing by 2. This will be a good opportunity for you to use shift operations that correspond to dividing by powers of 2. More on that appears later on in the spec. So once you've, in a C program, read that global variable, then there are a few ways to sort of look at the world and then affect the outer world. You'll notice in the pictures down here, there are 2 modes of operation. Either the battery level is displayed as a percent, or instead as a raw voltage value. And oftentimes there's a series of buttons or switches that will put some 1s and 0s into some sort of a status variable. And here we'll use the status port, BAT status port. A particular bit in there, the 4th bit, indicates whether a button has been pressed to put the display in voltage mode, or if that button hasn't been pressed, in which case it should be percent. I think I've reversed that, sorry. The button pressed should, you put it in percent so it's on, whereas if that particular 4th bit is off, then you show it in that. So here you'd have to be able to fish out that individual bit and ignore everything else in there, because there like to be non-zero quantities elsewhere. But if it's set, then you display something like this, the percentage. But if it's a 0, unset, cleared, then you would display this 4.23 business instead as a voltage. The formatting for that is just a little bit different then. So there's more description then of, so then the final part is, how do you actually create the display? Well, there's one integer called BAT display port that's essentially the light switches. That it starts out as all 0s, but if you flip a 1 on in it here, it will turn on the percentage sign down here. If you were to flip on the 1th bit here, it's off right now, but if you turn it on, then the V would show up as well. And you can start to imagine, the logic of this is like either one of these will be displayed, but not both of them. And according to the diagrams, the period should be on if this is in percentage, if it's in voltage, but should be off if it's in percentage here. And so this exercise becomes one of figure out what state the system's in, and then manipulate this integer by plopping down various 1s and 0s to show a display that represents the internal state of what's the battery level actually at there. There's a more verbose description of what each of the bits in this 32-bit integer BAT display port look like. And just sort of an enumeration here of 0, 1, and 2 control some special things. 3 to 9 are this rightmost digits. This is 10 to 16 are this middle digits, and so forth. And towards the end, then, there are some bits that lead or sort of raise this level, along with, at the top end, some unused bits. So this will make a little bit more sense as we start to look at how to start in on this problem. But there's some tips here then about how to go about writing each of these functions, and I'll encourage you to read through them. Primarily deals with a couple items. The first being, we'll model the state of the battery reader using a little struct, a BAT-T, and it'll have fields for millivolts and percents and the mode that it's in, either show in percent or show or not. And you'll have to create one of these in the first function, this set BAT from ports, by looking at those global variables and then doing some of the conversions mentioned. Now, bear in mind a couple things. In embedded settings like this, you oftentimes don't have certain niceties you might be accustomed to on your laptop, like a floating point unit. And so one of the constraints here is to use all integer operations. That shouldn't be a major issue because it'll be natural to sort of use percentage there. But in the interest of having quick updates, we'll also enforce that you understand how to do division by powers of 2 using shift operations. So avoid using division as much as possible. In some cases, it's unavoidable, like if you're dividing by 9 or dividing by 10, there's no shift equivalent to that. But dividing by any power of 2 can be accomplished with that, along with a few other tricks. And finally, eventually we're going to take this entire project and take the solution that you arrive at in C and convert it into assembly. So one of the goals for your code should be to make it as clean and short as possible, because the more C code you have, the longer winded your assembly solution is going to be. It's hard enough to write assembly, so the more you can make your roadmap in C easier to read, the happier you'll be later on for your future self that has to convert it into assembly. So code that's longer than 40 lines, which is a tremendously large budget for a tiny function like this, it may be penalized. Just be expedient, avoid nesting conditionals too much, etc. The next couple parts of the project here sort of describe what the other two functions you have to implement to make this. The main trouble will be in this set display from BAT, which is where you have to figure out where to put the bits through shifting operations. Read carefully the hints here, as lots of them will prove helpful. And just to sort of show what this looks like in practice, I'm going to stop talking about this web page for a second and bop over to the code. I've downloaded the Project 2 code pack over here, and so I'll unzip it in my Unix environment. You probably will have to do this on Grace if you don't have a local Unix environment, but I have one here, so it's a little bit faster to work. The main code that you'll be writing in is in bat update. Now there's no bat update file mentioned here, so we're going to have to create one. And I may as well do that now. Update, let's see, bat update.c. Not the test one, but a new one. Cool. And I'll probably want to include the project header here. This has a bunch of things, like we're going to have to use this this struct. It declares that these global variables that I'm going to need to read, they will exist. And it also gives me a list here of the three functions that I have to write. I could copy it here. I could also probably just zip over to the project spec and copy those so I can get these things here. The sort of commentary on it to remind me. So let me do that quick so that we're in good shape. Let's grab this one, so set bat from ports, and pop this down here. And as well, I want the other one here. Copy and paste. These are oftentimes referred to as prototypes or stubs. They aren't actual functions. They just declare that a function exists. But that's okay. We're going to give ourselves a little bit to work with on it and just plop down some empty definitions here. So this says it's supposed to return an integer up here, so I'll just return 0. Actually, I'll return -1. That's a typical failure. And do the same thing here. Return -1, and the same thing here. Now, if this goes well, I should essentially be in a position to run the test cases now, because I've fulfilled all the sort of typing information. These functions exist. They do absolutely nothing, but I could run test cases at this point. So let's just see if we make prob1 right now. Let's see. Oh, I got to change into the project directory. Let's see, p2 code. Make prob1. Let's see. Oh, let's see. This is an unknown type here. And that's because I forgot to include the header file. Like I said it was going to do it, and then I didn't. So this will be pound include the bat. I can't remember what it was. It bat 8h? Yeah, I got bat.h. Okay. There is a difference in C between including something with these double quotes and including something with the angle brackets, as such. For the moment, don't concern yourself overly with it. The short answer is angle brackets mean it's in a standard system header file directory. The double parens or the double quotes there means it's in this directory or nearby at any rate. And since this one is not often some Unix directory, it's right in this one right now, which should be good. So that'll make the compiler aware of, like, this is what a bat-t is, and that's used in several spots here, so we'd probably be in better order at this point. Hey, good, it compiled, okay. So I can run the tests, but I can also run the main here just to experiment with it. So bat main. If I run it with no arguments, it says I'm supposed to give it a voltage val. And I think that's a minor mistake, should be 0.005 volts. So let's try something like 7,000 for this thing, and I have to put it apparently in voltage or percentage mode. Let's try voltage mode. So that ran, and it didn't give me much here, but at least it's outputting some stuff. Generally, this main program can be used to experiment interactively because it'll call the first function to say, read the global variables, produce one of these structs, then take that struct and manipulate the display, and then tie it all together with this bat update, which will set globals according to what's needed. And you can see it doesn't do anything right now. That's because I haven't done much of anything yet in this code. It's incomplete. So start filling in sort of code there on it. As you'd want to know about what this is supposed to actually look at, like there's some examples of this in the spec that are a little bit lower. You can see here, it's like, oh, I compile bat main and I run it with something like 7,804 half millivolts. And this will go through a process with completed code to calculate, well, that would be this many millivolts, so it's divide by 2 basically. And that would correspond to 100% because it's above the 3,800 millivolts that would comprise a fully charged battery. The mode is 2, as indicated by the voltage part here. That's supposed to be a 2, apparently. And then the display will be constructed with correctly written code so that it looks like this. And each of the ones and zeros, you could be forgiven if you can't do it in your head, will be drawn down here then, as this is what it would look like on the actual display, at least simulated there. And if it makes sense, it's 3,942 millivolts, and you can see the 3.94 volts there with the last digit getting dropped, and you'll be responsible for doing a little bit of rounding with that thing. Now, all in all, this is going to amount to like less than 100 lines of C code between the three different functions that are in here. But it will take you a little while, possibly, to sort of recognize the patterns at play for use of bits, doing anding and oring and shifting and so forth there. But this is a useful set of skills and will equip you then to work in an embedded setting like this. I encourage you look at the remainder examples as they sort of show some of the edge cases as well of like 100% and 0% and so forth. For now, we'll move on to the next problem, which is debugging the puzzle box. I introduced this in lecture recently, so I won't go I'll go relatively quickly through this. The central idea is that you're given a program called Puzzle Box. It's not a normal program in the sense that you wouldn't run it but for an academic setting. But the idea is to use the debugger to figure out what inputs are needed to satisfy Puzzle Box. And the test cases associated with this will essentially just be like run with your input file, which has the answers that you've determined so far, and determine like how many points you get out of 30 down here. Now, quick giveaway, there are going to be 40 points available, so if you get beyond and into the last few optional phases, then you can earn some makeup credit, which is useful here. But not everyone gets there. Make sure to allocate time for this, but don't fixate on those last few at the expense of other parts of the project. This little input.txt file, I think, is provided for you. I think I have it here, and it defaults to this your directory ID 123. If I run Puzzlebox over here, let's see, let's build everything here. I can't make the last part yet. That's okay. So then there should be Puzzlebox in here, and I'll need to provide this input.txt file to it. And the first change that you'll need to make is that this directory ID is supposed to be your directory ID. Here at UMD, I'm prof K, and so I'll punch that in. And if I run again this time, then you'll see that prof K was actually accepted. It's used to generate a random number, which is the hash or seed value that's used to modify the inputs for your particular run of Puzzlebox. So that they're unique to some extent. This means the answers that work for you won't necessarily work for your neighbor. You're free to talk about the structural elements within Puzzlebox. Like, oh, I understand this phase is doing this, and so you need to figure out how to do that. But the specific answers, it doesn't matter if you share them because my numbers won't work for you. So to that end, as we discussed in lecture, the point is not really, I mean, you can look at the source code for Puzzlebox here, but a lot of it is intentionally sort of vague. So if it's divided into phases, and you'll work mainly with this phase 1, phase 2, phase 3. As you pass these, you get more points. The part that's intentionally obscure is that random number here. It's used to modify modulo 41, this a variable over here. Now, it's highly possible in cases like this to maybe guess and check, but take this as an opportunity to utilize some debugging skills and work through it in that fashion. To that end, if I jump back over to the shell over here, I'm going to fire up a normal shell. GNOME terminal. It comes up over here. I'll make this just a little bit bigger so that folks can read. And here, and the typical regime that we'll use is GDB. Its normal invocation, if I were to run it like this, is a sort of command line only thing. So typically, I'd run that with the -TUI option here to start it up. In case you forget, you can also, when you start up GDB normally, say TUI enable, and that will switch into this text user interface mode, where up top I see some source code, and down at the bottom you have the command prompt, which will allow you to do various things with GDB. Oftentimes the first thing you want to do is to set a breakpoint, because as you run through the program, you don't want it to run to completion necessarily unless you're chasing some sort of segmentation fault. In this case, I'm trying to work through phase 1, so we'll set a breakpoint there, break at phase 01. There are a bunch of different ways that you can set breakpoints, including line numbers or just typing break at the spot you're at. But breaking at function boundaries is a pretty good one. If I were to run at this point, which will start the debugger like running the executable, probably have to download a little info. Hopefully you don't have to do this. I'll get actually an error message because I forgot I have to put on the command line the input.txt. There are a couple ways to do this. If you want, every time you run, you can put an input.txt here. I prefer to set the command line arguments to be input.txt, so you don't have to remember that part. And then every time I type run now, it'll be like running puzzlebox input.txt. So around at this point, I get some screen tearing here, and so you'll be jamming Control-L a lot, which redraws the screen. The framework that's used to set this up, whose name still escapes me, I couldn't remember the lecture either. It's a little bit fragile, particularly as stuff would be printed to the screen. It'll cause this tearing and mishmash, but Control-L will redraw things so that you can see it. And you can see now I've stopped at a particular line where it's the first line of phase 1 where I set the breakpoint, and I can now start sort of doing some debugging. A common tactic for this is to not necessarily, I mean, you could step like I'll next this way, but I oftentimes say I'm really only interested at what happens here at line 277, so I'll break at 277. You can see the next little breakpoint sets up here, and if I continue, then I can jump immediately there and print out, oh, my A value is 26, my B value is 2, and my C value is 3. It was 1, but these 1, 2, 3 read from my input.txt file over, I guess I lost it. Here, 1, 2, 3. But my unique hash was used to modify A, so it became 26. Now, if I proceed, you'll see I don't make it into the return here, and failures, obviously you want to try to avoid those. So the next logical thing to do is to figure out how do I control like this condition, and what are the conditions under which I would make it to this return. So clearly you can control each of the ABCs. They're coming in as inputs from the text file, as well as then I just need to know the modification here for A. If it was 1, it becomes 26. I'm having 25 added onto it. So I can just pick a B and a C that reflect that part and make this set of conditions true. All right, so a little bit of reasoning is required here. Let's see, if A becomes 26, Then I'd want A to be less than B. We'll make it 50. And A should also, let's see, B should be greater than C, so we'd make it 30, and that would satisfy A less than C as well. So cool, okay. I've got my little stars down here, and again, I haven't saved yet, so I'll do so now. Save that thing, and I am ready to rerun. Irritatingly, on GDB in this TUI mode, up and down scroll the window with the code in it. And as you would want the command line history with that, it follows Emacs key bindings. So pressing Control P would go to a previous command. Control P again would scroll further back, and so you can keep Control Ping, or you can Control N to go to the next command in the history window there. So I'll back all the way up here to my run, or just abbreviate it with R for run. I always get prompted to say, do you really want to restart debugging? Because this will lose all the progress in your program so far, and I almost always say yes to that. So we're good there. With the first breakpoint, I'll continue just with the abbreviation C to the next one. If I print out A, it's 26. If I print out B this time, it's 50. And if I print out C, it's 30. So if I next now make it into the return, and I've just netted myself some points. So it'll bop its way back up to main, and eventually sort of step into the phase 2 if I use appropriate commands for that. I reiterate some of the advice that's given in the project specification, that you would do well to read some resources on debugging. I've used this particular exercise a number of times, and so I've constructed for an old class of mine a quick guide to the GNU debugger that's particularly oriented towards this puzzle box and a possible assembly level debugging exercise that we'll do later. So have a look at this documentation as you'd want to get hipper to the whole GDB scene. I think that's sufficient for the moment for Puzzlebox. There are 30 points available. The scaling for the points associated with each phase is in the source code, so you can have a look there. But for now, we're going to move on to the last and most challenging problem. So this business with problem 3 is to construct a small application. Interestingly, this application structure is to manipulate a data structure and to provide a little interactive command line experience for that. It's strikingly similar to a discussion exercise that we had done previously involving linked lists. And so one of the sage pieces of advice that you could follow would be to go grab that code and import it here. Import it, I mean copy and paste it into appropriate files. And that will allow you to get off the ground much faster as you start to develop this thing. The two main functions, or two main files that you'll be manipulating are treesetfuncs, which apes the list funcs that we had done in the discussion section, and treesetmain, which is the actual interactive part of it. That is very similar to the list main. It's over there. There's a header file that's provided, but the idea here is to create a tree set. If you've forgotten, sets are mathematical entities that are full of just unique items. They're relatively unordered, although trees oftentimes keep things in a certain order. A binary search tree is a great choice to implement one on account of it allows you in logarithmic time to determine, as I'm adding this new element, I need to check, is it already present or not? And if so, I just ignore that request. But if it's not present, then you allocate a new node and attach it to the tree and go to town there. It's my understanding that all folks in CMSC216 will have taken a course that discusses this as a topic. UMD's own 131 and I think 132 more so are supposed to do it, but you may not have had to implement one before, and so you do well to do a bit of review to make sure you're on track for that thing. At a high level, the way this application looks is after compiling the treesetmain and treesetfuncs with the Riot makefile, I can fire up treesetmain and get a little command prompt here with an initial help message that tells me, well, this is what the little application does. Now, there's some interesting things here, and we'll try to touch on several of them, but the most primitive operation is you start with an empty tree and you can add things into it. The commentary with the little hashes over here is meant for you to read. It isn't actually part of what the application is supposed to do, and it doesn't support any comment syntax. This is just there to illustrate some points about this. And examining cases like this, actual use cases, can really improve your understanding of what the application is supposed to do. So we'll add some folks in, add Lucas, add Mike, add Dustin, add Will, and add Al. You could ask what's the size of the tree right now. It's 5 nodes big, and that's on account of I added 5 unique things there. I can print the tree. And this is where things get just a little bit interesting. The printing will actually reflect some of the structure of the tree. The very first thing I added in was Lucas, so that becomes the root of the tree. It's indented the least over here. The next thing I added was Mike. Mike is alphabetically after Lucas. L precedes M. And so is going to go into the right branch of this tree from Lucas. Since there's no node there right now, Mike becomes the right child of Lucas. And so on and so forth there. Adding Dustin in, that becomes the left child of Lucas. And notice the indent here is about the same as Mike. And then Will is sort of rightmost over here, is it alphabetically last. L, as I do the binary search tree traversal, is left of Lucas, because E precedes L, but right of Dustin. And so L is the right child of Dustin over here. This drawing of the tree here is a little bit unusual, but there aren't a ton of other applications out there that draw it, but you can just mentally rotate this over, and Lucas is going to be highest up with a 90-degree rotation clockwise, and the other nodes in the tree will sort of be lower down according to how far they're in. If you're looking at specific paths, then you'd see things like this. So Lucas is at the roots. If I went right, I'd be at Will. If I went left, I'd be at L, and so on and so forth. As you'd have studied trees, there's several ways to traverse them. This is tantamount to an in-order traversal, although it's an in-order traversal that sort of goes right first, because Will shows up first in the printing. And as you would implement this printing functionality, you'll have to account for indentation. The farther down in the tree I go, the more I indent. And the functions that are suggested to do this, they will help you to sort of frame that sort of thing. There's also a pre-order traversal, which says print the root first and then do some things with the left and the right children. And this is nice because you can see, right up top, Lucas is the roots. Dustin and Mike are the children of that. Farther down are L and Will and so forth. Obviously, binary search trees support a find semantics, like go see if this particular thing is in there. Mike is, Nancy is clearly not. And then as you add things, Nancy is not present in the tree already, so it gets a little bit bigger. Hopefully all those things are not new to you. If they are, this one's going to be a real bear. If they aren't new to you, just expect it'll still be kind of a bear, because you've never probably had to deal with mallocing and freeing in a context like this, nor with pointers and sees structs there. A few other things that are worth noting. If Mike's already in the tree, if you add him, it's ignored, so the size of the tree does not change. And as well, later on, there's an interesting functionality that allows you to save the tree. So whatever tree is in memory at the moment, if you save it, it'll actually create a file called stranger.tree. And that allows you to eliminate the tree, which leads you to an empty one, potentially build a different tree, but then reload the original one, which nixes the current tree and then adds in the nodes that are read out of this file. It's extremely useful to recognize that, this pre-order traversal that we talked about up here, this Lucas followed by Dustin and Mike, followed by Al and Will, if you were to read things from a file in this order and add them to the tree, it would completely reconstruct the tree. So the pre-order traversal is going to be used during output to say, I'll walk through the tree in a pre-order fashion. As I see nodes, I will write them into this file. That's the saving functionality. And so when you load, it's just read and add them into a fresh tree, and voila, the tree is restored to what it was there. I think that's it in a nutshell. The next thing to talk about beyond the sort of high-level functionality is some low-level details. Clearly, trees will need some structs of some sort to operate on, and there's a provided tree.h file that is a header that gives you those, as well as lists out what the required functions are. You're free to implement more if you like, but I didn't in my solution, and the functions that are listed are minimal in the sense that if you're fairly savvy, you'll be able to get away with just the set that's there. Let's look at that provided header quick here. It is treeset.h. There's no documentation for these functions, but it's in the spec, so we'll look at it in a second. There's a minimal amount of documentation for the tree and the node. This is a very typical arrangement, which you're likely to have seen in like a Java class, where there's a class of sorts for the tree, but then a separate, possibly nested class for the nodes. In this case, we don't have classes and objects. We just have, oh, here's a struct that represents the tree. It has two parts: a node that's the roots and how many nodes are in it so far, as well as then a tree set node that deals with a left and a right branch. Being that it has to be a recursive struct, there's this slightly odd syntax for those here. Not needed for the tree set because it doesn't reference itself in here. And of course, what we're storing in here is just some nodes of sort, or sorry, some strings of sorts that are limited in size but sufficient for our purposes. Okay, down below then is a listing of all of the functions that you're required to implement in some fashion for this treesetfuncs.c file. This is the sort of back-end implementation of the tree, and there's a front-end main function then that will be used. And here's the point at which it's probably worthwhile to recognize, oh, there's a bunch of these functions. I'm going to need a main function. Let me go find some code that I can lift for parts of this at least. The first part is this treesetfuncs thing. Let me just copy all this stuff here as I did before. And I can create some empty stuff for that in my implementation of treesetfuncs. So here that file doesn't exist, so let me create it. treesetfuncs.c. Okay, so I've just pasted in the entirety of all those stubs, and we'll need to give them bodies like at some point here. That's fine. And then if I could try to roll my own main right now, but I'm feeling lazy but smart about this. And so I'm going to find the discussion that dealt with this linked list application and use that instead. So let me find over here, I216, the course web page. And let's see, I can't remember which discussion it is. Let's try discussion 2. That seems so. Yes. Okay, so there's a list main in here and a list funcs. So this is the discussion that actually deals with the application, which has the same exact structure to this. So because I don't have that one downloaded in this directory, let me just grab the link here. I'll use a good old wget. Actually, I'll see if this works here. It was not working earlier. Okay, good. That's there, but unfortunately it's like buried in this discussion too. We're gonna move this up a directory because I don't want to do it in my project 2 directory. So unzip discussion 02.zip. And if I look in my visual code browser, here's discussion 2, and here's my list main down here. Now, some of the command names are different over here. Like there's print and clear, if that makes sense. Exit, insert, well, that's kind of like add, get. Well, there's some thing that's equivalent to that in the tree land. There's probably a few others that I'll have to add into this and so forth. But if I'm looking for an interactive loop that prints a parent that says, ts pound instead of list bar here, or list caret, then this is a good start on that. So let's do the following. Use a little Unix command to say I'm going to copy what's in discussion 02 code, that list main.c. I'll copy that to my P2 code and call it treeset main.c here. So if I now come over to the project 2 directory and refresh, I've got this tree set main. It's actually the linked list stuff, but I can start renaming things in short order. One of the important parts of this is to be compatible with the tests. The tree set main application has to have this echoing functionality. You can discuss that or read more about it in the spec, but essentially makes it possible to say, oh, there's stuff coming in not from typed input, but from some file that the tests use, and that's spat out to the screen, so it looks sort of like someone typed it in. Not necessary for interactive use, but tremendously useful for testing. With that in mind, then, I think with tree set here, oh, we'll probably want, instead of list, we can have tree set.h up there. And there's probably a few other things that I might want to change, but that's, oh yeah, since there's all this list stuff in here, I'm going to have to do some commenting. Like this will be a tree set t, no doubt. And eventually this will be a tree set init, but I don't really want to do any of that right now. So let's just look wherever I see a list function. I'm just going to comment those things out here. Comment here and comment here. Now this is really a pot shot because I'm very likely not going to get a compile straight out of the gate here, but that's okay. It's like a good start on it anyway. Okay, so make prob3 now to see. Let's see. I got to get in the right directory again. And bring that back up. And I still have, the ith is undeclared, so that's at line 63. 63 is here. That's because I declared it here. So let's just say car ith equals null to begin with. It's probably not a, I mean, this is just to satisfy the compiler. I will need to make significant changes there in a second, but no matter. Let's see, and then this tree set list. Oh, it's an unused thing. So how do I satisfy that? Tree, I'll just comment it out because it's not used anywhere else. Okay, now we got problems here. Unknown type tree set. Oh yeah, of course, because I have two files here that is compiling. If I look closely, this is happening while treesetfuncs.c is getting compiled, and when I created that file, I forgot to plop down the header in it. So I'll copy it here because it's in main, and I'll change over to treesetfuncs and plop my header up here. How we do now? Hey, it compiles. So now I could run treeset main, and it looks a lot like the list one, but who cares right now? I'll exit out of that. I can also then make test prob3, and we'll start to get all kinds of failures here, but a lot of them can probably be easily resolved. For instance, if I look at this failure message, it's really just about oh, do you print the right help message that's shown over here? And I don't, and I don't have the right sort of command to quit and so forth. So to that end, no wonder I'm failing this test. I wonder if some nice professor happened to put the print message stuff in there for me to use. Oh yeah, it's right here. I could fix the print message by copying and pasting this into my code because it's sort of tedious to type all of that out. At any rate, this should allow you to get started to quickly get up and running those tests, and then start building functionality on it. As you would make modifications, the general regime is going to be to add in to treesetfuncs some of the code that you need here to get things done. And then over in your main, make use of that over here. By, for instance, initializing the tree, having a sort of crappy implementation of insert to begin with, and plopping that down maybe in place of the insert over here, although it'll have to be tied to an add command instead. So the big sort of difficulty associated with this part of the project is it's a little bit bigger and there are no unit tests. So the only testing that's done is whether or not this main program works right. I think it's important that students start to realize, oh, it's actually much easier to debug if there's a bunch of tests just for this one function. But there's a great cost to those. And it turns out to be quite difficult to say, like, oh, if all I'm doing is inserting, if I want to maintain the opaqueness of the tree type, I need some other function that allows me to inspect what's in there, preset find. And so tests for data structures oftentimes are, you have to get 2 or 3 functions more or less correct together before you can really test the data structure independently. And that's what this looks like, more or less. So be aware then that you'll need to work on insert and find and possibly the print function. And the print reverse order, I think, is among the most important to get right out of the gate. And that should allow you then to start proceeding and making progress on the tests. If any of those things are flawed, then it will take some debugging skill to figure out which one of those is flawed. Because the test might be failing because the insert isn't working right. It might be failing instead that the insert's fine, it's just you're printing it wrong. And you'll want to sleuth a bit on that part, possibly inspecting and printing out some outputs that's used purely for debugging purposes there. Okay, examples are further down, and as well there, as there were before, lots of tips on how to implement various things that are in here, including that main function. So take some time, make sure to allow yourself plenty of space for this. Come to office hours, ask questions on Piazza, and generally have a wonderful time putting this one together. That's all I got for now. We'll see you in lecture next week. Happy hacking until then.